Hello, my students. Now begins a brief introduction to our Chapter 6, which will focus upon chemical bonds. We just got done with the wonderful adventure that was the periodic table. We learned a lot about electronic structure, and now we're going to put it really into practice to understand why elements combine as they do. But if we just start to look at the world around us, we learned all kinds of things. Let's talk about oxygen for a moment. We are so familiar with oxygen combining with hydrogen to make water, and we're very familiar with all the properties of water. However, when hydrogen combines with nitrogen, it forms ammonia. Ammonia most readily is found simply as a gas, where we know at common room temperature and pressure, we know that water is found as a liquid with all its amazing properties. Well, why is water, H2O, a liquid room temperature, where H3N, ammonia, or NH3, exists as a gas? They're right next to each other on the periodic table. Shouldn't they be more common in their properties? Well, let's take another example. How about silicon when it combines with oxygen versus carbon when it combines with oxygen? Carbon with oxygen can provide us with carbon monoxide or carbon dioxide, both gases at room temperature and pressure, where silicon dioxide is one of the hardest substances that we know of. It's quartz. So interesting, members of the same family, when combined with oxygen, can create such varying substances. What about carbon itself? Carbon exists in 3 different forms: diamond, graphite, and soot. Those are allotropes of carbon. Why is that so? And why in the form of diamond is it the hardest substance known to man? Well, we can look at some other things. For example, when sodium chloride and chlorine combine, they form table salt. Table salt is a non-conductor in the solid state. However, it can conduct electricity as a liquid, but also when it's dissolved in water. Sucrose, carbon with hydrogen and oxygen, we know is soluble in water. However, it does not conduct as a solid in the liquid state or when dissolved in water. Why the difference? We are going to be able to answer so many questions like that this chapter. This chapter takes us through the journey of chemical bonds, and these are the topics of the chapter. We're first going to talk about what a chemical bond is and what are the types, and what properties are associated with the compound if we know the type of bonding that's holding it together. What are Lewis dot structures for compounds in the case of covalent bonding and ionic bonding? If we know the Lewis dot structure, we can actually predict the molecular geometry using VSEPR theory. We can predict if our molecule is polar, and then from that, what forces are holding it together. And that largely will explain many properties that we see. So first, what is a chemical bond? A chemical bond results from the mutual attraction between the nuclei and valence electrons of different atoms for each other. So if we have one atom, we know that its nucleus is content with the electrons that are there. However, it's usually desiring to gain or lose. Let's just say that it needs to gain some more to satisfy its octet. Well, when another atom comes along with nuclei, but electrons, well, this nuclei is not only pulling for its own electrons, but it also will start to pull for the neighboring electrons, and vice versa. This nuclei pulling for its electrons, and then it'll begin pulling for the atom's other electrons. These are going to come closer and closer and closer until a perfect distance is reached that will give minimal energy. That is what we call bond length. Now, we assume that there is some overlapping, but it's where this nuclei is attracting its own electrons, but also the electrons of its neighbor. Now, this attraction for the nuclei and electrons has to actually, overwhelm and be greater than the repulsion of these electrons for each other. So there's all kinds of forces interacting. But where potential energy is at its minimum, in this situation, that will give us our bond length, the distance between our nuclei in these joined atoms. Okay, and it lowers energy overall. What are the different types of bonds that we can interact with? Just find my next paper. All right. Well, we have 3 different types of bonds, and I bet that you remember this from maybe 7th grade, 8th grade, or previous exposure. Our 3 types of bonds are covalent, ionic, and metallic. The most simple way to tell the difference between them is by element composition. Ionic bonds are formed from metals reacting with nonmetals. Covalent are nonmetals with other nonmetals. Metallic are metals with other metals. So we can simply look at where elements are coming from on the periodic table. And if we have metals reacting with nonmetals, in the case of sodium chloride, that will give us an ionic bond. Where if we have nonmetals and nonmetals, in the case of carbon monoxide, that will give us covalent. And then, if we have metals with themselves or another metal, if they're bonded and not simply mixed, then it's a metallic bond. For example, if you have a large sample of copper, the copper atoms within that sample are bonded to each other through metallic bonding. So we can look at it through elemental composition. So, some classic examples of covalent: water, remember hydrogen is a nonmetal; sucrose, C12H22O11, carbon dioxide, there's just thousands and thousands. Ionic. Classic example, sodium chloride. We can also have iron 3 oxide, rust. We can also have calcium carbonate, limestone, and many thousands and thousands of examples. Again, usually it's metallic elements bonded with like. So if we have a sample of copper, a sample of iron, and so on. Okay, next. What is going on with the electrons? Let's do ionic first. We know that metals have very few numbers of valence electrons. Nonmetals, in general, have a greater number. And we know that metals will always lose their valence electrons. Nonmetals will gain, becoming anions. In ionic bonding, there is a transfer of electrons from the metal to the nonmetal. From the metal to the nonmetal. As soon as the metal loses the valence, it becomes a cation. As soon as the nonmetal takes the electron, it becomes an anion. They will immediately attract. Opposite charges attract. That is electrostatic attraction. That is the secondary most powerful force known to man, second only to the nuclear force. Very, very strong force of attraction. Opposite charges attracting. That is what holds, in the case of sodium chloride, the sodium to the chloride. The sodium takes on a positive charge, the chloride takes on a negative charge. What about the case of covalent? Well, if we have 2 elements coming together, let's just say we have fluorine and it needs to bond with chlorine. Well, we know that fluorine brings in 7 valence electrons. Chlorine brings in 7. Each needs an additional. Well, he needs 1 more and he needs 1 more. Well, what if this fluorine would share an electron with chlorine? And vice versa. Chlorine would share one of its with fluorine. Oh, isn't that so nice? So it's not a transfer, it's not a give and take like ionic, it's a sharing, and then everyone wins. In covalent, there's a sharing of electrons between the nuclei of your non-metallic elements. In metallic, if we have a cross-section of copper wire, we know that metals will only and can only give away electrons. Copper has 2 valence. To get the 8, it needs to give away 2. So if it gives away 2 electrons, it forms a positive 2. Gives away 2 electrons, forms positive 2, and so on. Now, we've gained electronic stability. However, we can't just have a sample of copper plus 2. It needs to be neutral overall. So copper is content having given up its electrons, but yet it needs them to maintain electrical neutrality. So, in metallic bonding, the electrons do not have a home. Here, the metal gives to the nonmetal. Here, they're shared between elements. Here, the electrons are free to roam between all of the cations. We call metallic bonding a sea of electrons. The electrons are delocalized. They do not have an official home. So that gets us started looking at chemical bonding.